In this session, we want to continue to look at the relationship between work and energy. As we saw in a previous session, we could connect up the change in kinetic energy, which is the energy of motion, with the work done on an object. In this session, we want to show that we can develop a similar relationship between work and potential energy, and then derive a more general expression for the work energy theorem. So this session is titled the Work Energy Theorem and Potential Energy, and let's launch into this. So first of all, recall what we defined as potential energy. This was energy associated with the position of an object in a force field, such as the location in a vertical sense of a mass, m, being influenced by a gravitational field, and that mass m has a weight mg, so that's the force of gravity on that mass. And if that mass changes its position from one location vertically to another location, then the potential energy has changed from the value of the original location of mgy0 and to a final value of mgy at the new location. And as a result of this potential energy, we know that the object is capable of, say, falling a further distance, capable of reaching a higher kinetic energy. And therefore, as a result of the idea that energy is not created or destroyed, that it must have had energy even while it was at rest at a higher level, and that energy was not yet evident until it was released to fall. Therefore, we called that energy potential energy. And we listed a couple of different forms of potential energy that we were going to be using throughout the course, one being gravitational potential energy, where the potential energy is a result of the force of gravity acting on an object, and a spring potential energy, where the potential energy was a result of the spring force, Hooke's law kx, acting on an object that the spring was exerting its force upon. We defined the potential energy as the symbol capital U, and of course, as usual for energy, it has the units of joules. We saw also in a previous session that the work energy, there was a relationship between kinetic energy and work, which was shown to be the change in kinetic energy. K with no subscript is the final kinetic energy, and K with the subscript 0 is the initial kinetic energy. And so the difference in kinetic energy for an object is the result of work being done on that object, either work being done to speed it up or perhaps work being done to slow it down, such as friction acting on the object. And so the change in kinetic energy is attributed to the work done on that object. Again, recall that this is a situation where we are looking at who is doing the work, and that is who is exerting the force or influence. That is the agent, as the person that is performing the work, and then who is the work being done upon. So that is the object whose kinetic energy is changing. Remember that the definition of kinetic energy in general was 1/2 mv squared, so we could also write this work energy theorem in a form using velocity and mass, as shown here. Well, in a similar manner, this particular derivation was restricted to objects which are moving without changing their elevation, so just moving in a straight line at the same relative elevation, and therefore there's no change in potential energy to be considered in this case, just simply a change in velocity which resulted in a change in kinetic energy. Let's look at a situation in which we have a change in vertical position and therefore a resulting change in potential energy. So this is the scenario. We've got a book on a table. As a result of the book being on the table, we know that the table being above the floor and the floor being our reference level where we will measure all potential energies relative to that, so the floor is 0. So the potential energy of the book on a table of height y0 is given by mg, the weight of the book, m times g, times the height. If then we take that book and we place it slowly onto a higher shelf on a bookshelf to a height y, then we see that the potential energy has increased to mgy, where y is bigger than y0. Therefore, the potential energy has actually changed. We have a potential energy difference. The new value minus the old value. Now recall that I said that this process was accomplished by you taking the book and slowly raising it up to this higher level. So someone had to do work in order for this to happen. And let's manipulate this final equation a little bit to show who that is. So we have this equation previously where the change in potential energy was mgy minus mgy0. We can factor out the common factor of mg and collect the difference in height, y minus y0, in parentheses. Notice that mg is just the force of gravity on the mass m, and the change in y is now replaced by just delta y, and that's a force times a distance, which is the definition of our quantity work. So we see that the change in potential energy was accomplished by work done on the book. The book's initial velocity was 0 at the table. Its final velocity is 0. We did this process very slowly, so we didn't add kinetic energy to the system. So the only thing that changed during this transformation was the object's potential energy. And we see that in order for this to happen, work had to be done. You, the agent of the force, you are overcoming the force of gravity, lifting the book up slowly, exerting the force on that book of mg, opposite to the direction of gravity, and you do that work over a distance delta y, and you impart that energy to the book in the form of increased potential energy. Now, it doesn't have to be gravity. We can be doing work against any force or with any force, and that work will result in the potential energy change of the object that the work is being done upon. If we're using a spring, and we know that the potential energy of a spring is given by 1/2 kx squared, then if we change the extension of the spring from some beginning value to some final value, then in order for the potential energy to change from its beginning value to a final value, we have to do work on that spring. Perhaps to stretch the spring from 10 centimeters to 20 centimeters, we would have to exert a force over that distance. The force would be equal to the average value of Hooke's law over that distance, and we multiply by that distance, and we get the potential energy, the additional potential energy that's stored in the spring as a result of the work being done. And we saw that the same applied to the gravitational field, where we have a constant force, and the potential energy varies linearly with the height. So in general, then, we've developed two relationships here that we want to sort of combine together to have a general work energy theorem. We found before that work was related to the change in kinetic energy, and that involves situations where there was no change in position or height in the gravitational field. So all we had to consider ourselves with was changes in velocity. We just looked and saw an example of changes in potential energy relating to work, where there was no changes in velocity of the object that was being moved from one position to another in the gravitational field. So obviously with those two relationships, why not combine them together to accommodate all situations and say anytime you see a change in kinetic energy or a change in potential energy or both, you can ask the question is, why is it happening? Because there's work that has been done by an outside agent on the object that we're looking at. So the consequences of the work-energy theorem are that energy is still conserved, and that is we aren't creating energy out of nothing or destroying energy. We just simply have an agent, someone who's exerting a force, something which is exerting a force, such as gravity, a spring, or perhaps you pushing or pulling. You are acting on the object. As a result of your actions on the object, or gravity's action on the object's kinetic energy may increase as it falls faster and faster. The object's potential energy may increase if you're raising it up, or it may decrease if it's going down. But in some fashion, the combined effect of the work being done is to change the kinetic and or potential energy of the object. So that if an external agent does work on an object, you wouldn't expect the energy of the object to stay the same, because that external agent may be imparting energy to the situation that was not there prior. Now, that means that there still is conservation of energy going on, because the agent responsible for this work has expended energy. That energy has been given to something else, so there's a conservation involved between those two systems, the agent responsible and the object receiving the energy. So this is our general work-energy theorem, that work is equal to the change in kinetic energy plus the change in potential energy.